We're in 10.4 of Barnett, and this section is entitled The Derivative, and it is one of the key concepts in our class. So it is really important to understand this section. We'll spend quite some time on it, making sense of the derivative. So you'll be able to calculate things like rate of change, slope of a tangent line, interpret the meaning of a derivative, and identify the non-existence of the derivative. That's the goals for this section. We'll start by introducing something called the rate of change. So given some function f of x, the average rate of change from one point x equal to a to another x equal to a plus h is simply given by this quotient, f of a plus h minus f of a over h. You could sort of think of this as the vertical change over the horizontal change if you think of it visually, and that's why this is called the difference quotient and also the slope of the secant line. That's how it's interpreted visually. For that, let's take a look at this picture. If we have 2 points on a curve, P and Q, such that the coordinates of P are a comma f of a, and the coordinates of Q are a plus h comma f of a plus h, then what we have here for the difference quotient is simply the slope of the secant line. It's the line going through these 2 points. That's what we call the secant line. The line going through 2 points of a curve. It might be hard to see here, but this is actually the curve y equals f of x. It's this curve over here. Okay, maybe I could darken it a little more just to make it stand out. And then we have this line going through our curve at these points P and Q. Okay? And as you can see, this is the vertical change, f of a plus h minus f of a, over the horizontal change, the h. That difference quotient represents the slope of the secant line. It also represents average rate of change. It gives us the average of how things change. Okay, so the slope of the secant line through P and Q is the average rate of change. So as an example of this, think about the revenue generated by producing and selling widgets given by this function, r of x equals x times 75 minus 3x, where x is between 0 and 20. What is the change in revenue if production changes from 9 to 12? So you're producing 9 widgets, you'd like to produce 12 widgets, and you'd like to see how will revenue change based on the change in production from 9 to 12. Well, to do that, you take a look at the change R12 minus R9, and that gives you 36. How did we obtain these values, 468 and 432? We used the formula for R of x and plugged in 12 for x and 9, respectively, to obtain 468 and 432. So increasing production from 9 to 12 widgets will increase revenue by $36. Okay, so the revenue is, that formula again, what is the average rate of change now, says the question, in revenue per unit change in x. That's what that means. So what is the average rate of change in revenue if production changes from 9 to 12? Compare that to the earlier question, which was just what is the change in revenue alone, right? So change in revenue could be denoted this way, and that was just R12 minus R9. Now, in the next example, we're looking at average rate of change. In other words, the change per unit in x. Okay, and to find that, once again, we have to do R12 minus R9, but we have to divide the change in revenue by the change in production, right? In other words, 12 minus 9, because we went from 9 units to 12 units. So even though we still have that $36 increase, now we divide by the number of widgets that we've increased production from. So that will be 9 to 12, that will be 3. So 36 over 3 is 12. We say the average change in revenue is $12 when production is increased from 9 to 12. Okay. Now let's talk about the instantaneous rate of change. How is that different? We'll consider the same function that you had, y equals f of x, but we're only going to focus near the point P, which has coordinates a comma f of a. Then we look at the difference quotient again, f of a plus h minus f of a over h, where h is different than 0. That gives us the average rate of change, as we know, of f over the interval from a to a plus h, right? Just like before. Well, we're going to take the value of h and make it smaller and smaller. So in the limit, we obtain that the instantaneous rate of change is given by this exact formula. The limit, as h approaches 0 of the difference quotient, that gives us instantaneous rate of change. So all we're doing visually is we're taking our point Q that we had before, and that Q was at the coordinate a plus h, if you remember, comma f of a plus h. Well, all we're doing is we're making h approach 0. We're shrinking the distance between P and Q. So we're sort of moving this point Q along our curve and making it approach point P. And there comes a point in time in the limit that this point Q almost becomes point P in a way. So the secant line, the line joining P and Q, becomes a tangent line. A line that touches the curve only at one point. In this case, it will be the point P. Okay, so this secant line became a tangent line when we took the limit as h approaches to 0 of the difference quotient. So remember, the slope of the tangent line is simply the instantaneous rate of change. It tells us how this function changes at that instant when x is equal to a. Okay, so to get a formal definition here, given some function f of x, the instantaneous rate of change at x equal to a is simply the limit as h approaches 0 of the difference quotient, provided that limit exists, obviously. It can be interpreted as the slope of the tangent at the point a comma f of a. Okay, and then you could see the picture again. It's the slope at this point, a comma f of a, the point P. That's the slope of the tangent line, this line here. Okay, if that's how you interpret it, the slope of the tangent line, that's instantaneous rate of change. Okay, so why don't we take a look at another definition now, the more popular one that we'll need and use in this section, and the big one in our class. So for y equals to f of x, we formally define the derivative of f at x, denoted by f prime of x, right? We put a little prime there. We say that this is simply the instantaneous rate of change, or the limit as h approaches 0 of the difference quotient f of x plus h minus f of x over h, provided that limit exists. Okay, so if f prime at some point a exists, then we call f differentiable at that point a. If f prime of x exists for each x in an open interval a to b, then f is said to be differentiable over that whole interval, a to b. Alright, so how do we interpret the derivative? What does this derivative mean? Well, if f is a function, then f prime is just another new function with the following interpretations. For each x in the domain of the derivative, f prime of x is the slope of the line tangent to the graph of f at the point x comma f of x. For each x in the domain of f prime of x is the instantaneous rate of change with respect to x. Okay, and finally, if f of x is the position of a moving object at time x, this is from physics, then v equal to f prime of x is the velocity of the object at that time. So this function also represents velocity, which is the derivative of position in physics. And there's several ways to find the derivative. We're going to spend some time in the next section of this chapter talking about them, but for now we're going to introduce this four-step process. We're going to call it the four-step process. So find f prime using the four-step process. Since f prime is this limit, the four-step process essentially builds up to finding this limit. So what you do is first you find f of x plus h, that's step 1. Then you find the difference, f of x plus h minus f of x, step 2. Then you divide that by h to get this quotient in step 3. And finally you take the limit in step 4. And that's how you obtain the derivative using the four-step process. Let's do an example of this. Find the derivative of f of x equals x squared minus 3x. Let's use the four-step process. So step 1 would be to find f of x plus h. And what does that mean? It means every time I see x, I'm going to replace it with x plus h. And let's see what I get. I get x squared plus 2xh plus h squared minus 3x minus 3h. Okay. Step 2 was to look at f of x plus h minus f of x. Right? I'm building up to this definition here. Always remember this formula in the back of your head. This is what you're working with. The limit of the difference quotient. That gives you the derivative. Okay, so I'm building up towards that. So I have to subtract f of x. And if I do so, I get x squared plus 2xh plus h squared minus 3x minus 3h, right? That's just the first part, f of x plus h. That's what we have here. Double underline those two because they're the same. From that, I'm going to subtract my f of x, which is x squared minus 3x. So when I subtract x squared minus 3x, the signs flip and I get minus x squared plus 3x. And you see that's going to create for some cancellations here. the negative 3x and the positive 3x will also be gone. So what do I really get here? I get, well, I get 2xh plus h squared minus 3h. That's all that's left. Okay, the rest is gone. In step 3, all I have to do is take this quotient and divide it by h. So I'm going to put step 3 and 4 together here, right? Essentially, I'm just taking the limit as h approaches 0 of this thing all over h. And what do you notice? In the numerator, there is an h that you could factor out because all the terms have an h in them. So this is 2x plus h minus 3 all over h. And I forgot to write limit as h approaches 0. Make sure not to make that mistake. These cancel. So now we have the limit as h approaches 0, limit as h approaches 0, of 2x plus h minus 3. So you can evaluate this by plugging in 0. You get 2x minus 3. So that's the derivative of x squared minus 3x using the 4-step process. Here it is one more time on this slide, a little clearer, typed out so that you could double check the work. And you could pause the video here if you'd like, double check the algebra, the arithmetic, make sure everything is right before you move forward. Okay, so one other example, find the slope of the tangent to the graph of f of x equals x squared minus 3x at x equal to 0, x equal to 2, and x equal to 3. Well, to find the slope of the tangent, right, find the slope of the tangent, this is sort of like saying find the derivative at those points. That's what this means, because those two are equivalent. The derivative and the slope of the tangent line are equivalent. We already know from the previous example that the derivative for that function is 2x minus 3. All we have to do is plug in 0, 2, and 3 for x to figure out what the slope of the tangent would be at each one of these 3 points. And that's what's done on this slide here. Okay, one last thing to show you here. Most graphing calculators have a built-in numerical differentiation routine that you could use. And let's take a look at how that works. We know that the derivative is 2x minus 3. And then we already found out that at x equals to 2, the derivative was 1. So they want us to verify in this slide on a calculator how this works. And you could use several commands to do it. Let me show you how to do that. Okay, so I go to my calculator's y equals editor, and I type in my function, x squared minus 3x. So I have x squared minus 3x. Alright, I hit enter, zoom, and I'm going to use the standard window here, option 6, zoom standard. And here is my graph. And then what I'm going to do afterwards, as pointed out on this slide, I'm going to use dy dx under the calc menu. So I do second and calc, which is really the trace key when you do the second. And look at option 6, it's dy dx. I hit option 6, and then I type in 2, and that will give me the derivative at 2. And surely enough, it says dy dx is 1, so the derivative there is 1. And that's how we obtain this over here. Dy dx, by the way, that's another notation for f prime of x. Okay, it's called Leibniz notation after a mathematician named Leibniz. So that's how you get that the derivative is 1 using your calculator. It's the slope of the tangent line. Okay, so anyways, here's another problem to practice using the 4-step process. Once again, make sure, do this on your own, then pause the video and check the steps. Make sure you're doing it correct using the 4-step process. Okay, first you start with f of x plus h, then you do the difference, then you divide by h, and then you take the limit. Alright, and when does the derivative not exist? Well, obviously the existence of the derivative at a depends on the existence of this limit. When x becomes a, right, this is normally x, now it becomes a. If the limit doesn't exist, we say the function is not differentiable at x equals to a, or simply f prime of a does not exist. Okay, so when does that happen visually? When your function has a hole or a break at that point. If it has a sharp corner, like absolute value of x, okay, then the derivative there doesn't exist. Or if it has a vertical tangent, here's an example of that. If you have a function that has a vertical tangent line, something like this maybe, then the derivative does not exist there. So here's a summary slide that you could take a look at as you review this section. Make sure to watch all the other videos available that I will post for this section.